So today is April 23rd. Okay, so hold on. Do this. Okay. Um, we're going to cover um, something new today. Uh, Last time we introduced one method, a constraint optimization method for uh, with linearization. So we did spend some time on my lecturing to solve a problem, but I made some calculation mistake, so I couldn't get the right answer. And I think one of the students sent a comment to the Facebook and let me know where I made a mistake. So I'm happy that someone was able to find a solution, and I hope everyone found found my mistake in your homework. Today we're going to cover something further. What if at some point we don't want to rely on linearization? Because we know when we linearize something, the approximation of the functions may not be accurate. So probably when you linearize all your functions at the end, what you get may not be a good solution. So today we're moving on to nonlinear optimization. But I'm not going to introduce you the most complicated method. We are moving on little by little. Okay, so at the first couple steps, we still will have some portion of linearization, but some other portion in our formulation, we start to introduce nonlinear part. Okay, so before I introduce some methods, we need to understand something called KKT condition. So what does KKT mean? KKT actually represent three person. Let me find my notes. Okay, so we're going to talk about something called KKT conditions. And if you are interested, who are those KKT? You could actually Google it. KKT condition. Karush Kun Tucker. Basically, three mathematicians. Okay, so you could always look for references from internet. So Karush, uh, Kun, and Tucker. Okay, so these three person developed this KKT condition in the past. So what does this do? KKT conditions help you to evaluate if some solution point is already optimal in a constraint optimization problem. So it's quite powerful. It's several conditions that you could check, and when you are able to satisfy those rules, uh, you have very high chance that the solution is optimal. Okay, it's not a uh, iteration method. It's a, condition checking procedure. Okay, so let me today in the first half, I'm going to introduce this KKT conditions. So let's start with a general formulation, a general optimization problem. So this is like a very general optimization formulation where I have one objective function f, and I have a bunch of equality constraints h, and a bunch of inequality constraints g. And I use the index I to represent the number of your equality constraint, and I use the index j to represent the number of your inequality constraint. Okay, so this is very standard. And to introduce some of the things I would like to talk about, we actually need to reduce the problem and focus on some of the things that we work on in the past. So then we come back to this general problem later on. Okay, so today we wish we are able to talk about the KKT conditions that is able to check a design point, which if the point is optimal solution for a general problem like this, or maybe it's not. Okay, so to derive some of the equations from KKT conditions, actually we need to talk about reduced problem. So in a reduced problem, or a problem that is having a different format, where I only have equality constraints, if I have a problem that only has equality constraints, then let's see what will happen. And this is actually very similar to our linear programming formulation, because we use slack variables to convert all the inequality to equalities. So this is very similar to what we had earlier. But over here, we don't necessarily mention whether f and h has to be linear or nonlinear. Okay, so it's a little bit different. Okay, so let's say I have a design point called xk. Okay, and in the design space, I would like to move on to a new position xk plus 1. Okay, so in uh, most of the methods that we introduce right now, we would like to find a new design point based on some design point that we know in the past. So that's called the movement from the previous point to the new point as a vector of d. So d is like a movement vector, right? And suppose this is a feasible point. Suppose this is a feasible point. So this point is satisfying your constraint, but it's not the optimal yet. It's just a feasible point. Okay, so when we uh, when we have this set up, of course, we wish what do we wish? We wish um, when we find a new point, and of course, it has to satisfy our constraint, right? When we plug in into our constraints, of course, uh, they I wish we wish them uh, those points, this new point will satisfy the equality constraint. So we could actually rewrite this as the O point plus D, right? Because the new point basically is the O point plus our movement vector D. Okay? So if you have no knowledge of optimization, you have no idea how to perform minimization in a systematical way, you could actually do this. You could just start from somewhere. As long as it's a feasible point, you can start to move little by little, one step by one step. And as long as when you move on to a next position and it's feasible, then it seems like you can continue this process until you couldn't find a better point. Okay, so this D movement could be a very small step. Okay, so based on this concept, um, we would like to also uh, do further analysis and see if we can get some unique equations later on. Okay, so here that's just keep in mind. We wish we wish this is happening, but in order to talk about what I'm gonna say, we need to switch to another equation, which is Taylor expansion. So we can always do Taylor expansion. Okay. So now, if we do Taylor expansion of your uh, of your f of x, and what would your f of x could look like? Um, so your f of x k plus 1 could be very close to the following equation, where you can treat your previous point as your expansion point, and then you will be having this. Since you are focusing on f function right here, and then your variable is your uh, k plus 1. So over here, of course, I'm using my variable to minus my expansion point, right? So this guy should be the same as this guy. These two should be the same because this is my variable and this is my expansion point, right? And over here, of course, I have dot product, and then we have the gradient. let me do gradient. So like this. Okay. And since we know about this, the new point is my previous point plus the d vector. I can plug in those information into my Taylor expansion. So I have a new equation like this. Um, so f of x k plus 1 equals to, here I would like to use the same thing, basically the same thing. And here, since uh, k plus 1 minus xk plus 1 minus sk should be my d vector, right? This is my d vector, okay? And on the right hand side of this, basically a dot product. So only difference I have here is basically my this term become d vector, okay? And similarly, let me move this guy to here. Okay. So similarly, we could apply this same concept, this derivation to our equality constraint. So our equality constraint could be each one of them. The jth equality, ith equality constraint could be written as follows. Here I should have something like this, plus that movement vector, and then gradient h I x k. I should have this. And of course, I wish this is 0, right? Otherwise, I move on to some new point that doesn't satisfy my constraint. I can no longer uh, move forward. Okay, so suppose we have this. And look at this one. Here, this guy is actually 0 because originally I said we start with some feasible point. So supposedly that feasible point is satisfying my equality constraint. So of course this term will be 0. And we wish on the right hand side, we wish the whole equation becomes 0. Then we got something interesting. We derive some equation like this. The dot product of d and the gradient of h equals to 0. So if you could have something like this, probably that d vector could be the right vector for you to move from the current point to a new point so that your new point still satisfy your equality constraint. Okay, so if you are able to have this property that satisfy this equation. So that's actually something that we didn't know in the past, but that actually will be one of the important equation in KKT condition. Okay, so let's see. Okay, how about the objective function? So when we try to Um, so if we are able to satisfy this new equation, it's like we could maintain a very important property in optimization process, which is feasibility. Okay, so when you people ask you, hey, you have learned optimization, can you tell me what does most of the methodologies have in common? Well, basically, those methodologies tries to keep the feasibility of the point. If the method will take the point to somewhere, but the new point become invisible, so the new point doesn't satisfy the constraint, then the method may not be a good method because uh, probably the method cannot take the design point back to the feasible domain. So usually most of the methods tries to keep the feasibility of their design points. Okay, and there's another very important uh, property or functionality of optimization methods usually have, which is trying to stay trying to maintain optimality. Another property. So what does optimality mean? Optimality means the methodology tries to find a new point that it better be better than the previous one. So if you could find a new point that is a feasible point, it's a satisfying point, and it's better than the previous one, we think it's a good method. As long as you have enough time, resources, eventually you probably could find the best solution, right? So uh, how can we keep so-called optimality? Here is one suggestion, which is came from here. Okay, so when we do the Taylor expansion of our objective function, the first term basically is the function value at the current design. When we have a current design, and we could calculate the function value, but uh, whenever the design point is chosen, this function value doesn't change at all. So what will change the function value basically come from the second term right here in the second term. So only the second term has opportunity to change the function value. So if we could have the second term that makes the function value lower and lower, that would be nice. Otherwise, if the second term is zero, you don't make any improvement because in your new design, your function value is still the same. You are not following the optimality because you didn't try to find a better design. You find a design that has the same quality, same performance. If you have your second term which is positive, that means your function value become greater. So actually you have a worse design. So in order to have a better design, which means your new design is having a lower function value, the second term should be, or we wish the second term would be negative. Okay, so that's why this part has some other discussion right here, which is this one. We wish to be negative. Okay, so that tells us the uh, moving direction, and dot product with the gradient of your f, we wish this is 0. If this is 0, sorry, negative. If we could find a new point such that my moving vector d dot product my gradient f is negative, then I'm making my function value decreasing. So I am trying to find a better solution. So this is how you could keep optimality. So optimality and feasibilities are two properties most of the optimization methods needs to maintain. Okay, so let's now we learn something new about uh, optimization, which are these two very unique equations and also two special properties. Okay, um, next we would like to do something further. Let me see how I get this one. So, I think we need to have some arguments about these two equations in order to introduce the next statement I would like to talk about. So let me copy this part and move on to the next page. Okay. Okay, we have these two properties for optimization. Um, if we have, let's say, if we find D, what is D? Basically, a movement from the current point to a new point. If we find a D that satisfy, let me call this equation 1 and this equation 2, okay? So if we are able to find some D that satisfy, oops, it's blocking, satisfies 1 and 2, okay? So what does that mean? That means the new point is still a good point, and also it's making me, it's actually better design the current one. Okay, so it's good, but uh, it may not be the, it's possible it's the optimal. It may not be the optimal, right? We don't know. We just know it's a better feasible solution, right? So this means x k plus 1 is a better and feasible point. Okay? Can we have some other argument? Can anyone think of? Oops. Oh, yeah, that's fine. Okay, so when we have arguments or we have observations, we don't always observe what we get at the end. We can also observe what we had in the beginning, right? If this situation is happening and we have the argument that the new point is good and it's feasible, What does it also say to our original one? Can anyone tell? So the original one is not optimal because you found a better one. That means your current one is not the optimal. That confirms your current one is not optimal. So that's also something, right? So that's another argument you could make. The current one definitely is not optimal because you already found a better one. So your old one definitely not optimal. Okay? So if we have this kind of argument, can we reverse the argument uh, and see what's gonna happen? So let's have a reverse discussion. So if I found another argument, if uh, xk is already optimal, okay, then it seems like the statement one and two cannot be satisfied at the same time. Okay, so let's think about this. One and two cannot be satisfied at the same time. Okay, so if the current one is already optimal, your statement one cannot be satisfied. Or let's say, if I think let me show you a graphical way. What does it mean? Let's say I have this some constraint G1 and another one G2. Okay, and I'm using the hatch to represent the wall, so you don't go to the wall, right? So what would be my design domain? This area. So this right hand side is my feasible domain, right? Okay. Even though we are, I'm sorry, actually we are talking about equality constraints, so I better make a different statement. Sorry, let me delete this. So how about this? I have a h function, and I have my oh, how about this? Let's make it more realistic. So let's say my full drawing. Hold on. So let's say I have a nonlinear h function. Okay, so any point on top of this curve is a feasible point. Okay, and let's say I have a contour of my objective function f, and this is descending the descending direction, which means when I move along this direction, my function value drops. Okay, so let's say this is a point xk, and if I can move to a different point here, xk plus 1, then what would be my vector d? So basically, my vector d is right here. This is my vector d. And uh, if you if you So actually, in this case, it's the first statement. This case satisfy my first statement because I was able to find a better point because the function value drops, and also my new point still satisfy the constraint. Okay, so that's my satisfying my argument first, the first argument. So my new point is a better and feasible point. My old point is not optimal. Okay, so how about the other situation? The other situation is like this, where I probably is already here. My actually by observation, you can tell this function point is already at the most left endpoint position on this nonlinear curve. So supposedly the function value of that point should be the lowest on the curve, right? And if you would like to find another point that is feasible, so any point other than this xk will have a lower function value, right? So if any other feasible point, so for example, this is another feasible point. So when you have another feasible point like that, it's actually having a worse design. So your moving direction D is like this, and this is actually a worse design. So if it's a worse design, then it won't satisfy. So the rule one doesn't satisfy. Okay. So how about another point? Let's say I found a point somewhere else, like here, outside of the curve. And because I move outside of curve, my function value could be lower. Okay, so it's a better point because function value is lower, but it's not feasible. Okay, so in this case, it become infeasible. So this situation, your rule number two not satisfied. So it seems like in this argument we can tell if xk is already optimal, the first and the second statement cannot be satisfied at the same time. Okay, so that's quite interesting. Um, so this actually leads to further discussion and a new equation, and that it is able to uh, that help us to uh, explain what actually was discussed. But that new equation is not that the is not straightforward. So you may need to think about it. Okay. So let's see how we could make it so much easier to understand the next equation. Let me figure out how to make it a easy one. Because that this equation actually is very quite important. Um, so the gradient. Okay, so let me just explain by showing you. But before I show you, let me now tell you what's the equation I'm going to talk about right now. So there is this new equation look like this, the gradient f, and here I plug in my optimal already. And then what does this equal to? This will equals to summation of lambda I times gradient h I, and over here my optimal. Okay, and this require, like I said, it's not straightforward, but if I show you, you could find, oh, this is quite interesting. So let me make this equation 3. Okay. So the difference between equation 3 then 1 and 2 is that in equation 3, we put the gradient f and gradient h together and formulate a linear combination of everything. And inside this equation, I claim my design point is optimal, so x star. And I said the left hand side should be equal to right hand side. Okay, and let's see what's happening. Okay, so if I so in this case, this is talking about our last argument. Basically, my design point is already optimal. Okay, so if I try to find a movement vector d, and then let's operate the calculation of 1 and 2. But this time when we do it on top of equation 3, and let's see what will happen. Okay, so I would like to talk about this on the next page. Okay, so let's just try to do something that will help us to understand this. So let's have a d vector and then dot product with the entire equation 3. So the left hand side basically is this, and the right hand side basically. So this is my left hand side. Okay, and my right hand side uh, is basically um, summation of I lambda I, and it's let me expand this whole thing. So, so it's gonna be like lambda I d dot gradient h1 x star plus da da da. How many h do we have? We have m of them. So this is lambda m d vector, and like this. Okay. So if this d will help us to find a feasible point. So let's say if this d uh, helps us find a feasible point, then we should satisfy the rule number two. So uh, all the let me see if that is a good. Um, okay, let's try this. If this so so it will satisfy number two. So the entire right hand side will become zero, right? Because all the d dot gradient h term becomes zero. Because if this that's a feasible point, so the right hand side become zero. And uh, in that case, if we wish, if equation three holds, then my left hand side becomes like this. Then um, I think this may not be an easier way to explain. Let me try to use what I had on the notes, but my the one on my notes may I hope it's easier. Okay, let's say three. So if three is not true, okay, let's say three is not true. Okay, so we could express this equation into a different way. If it's so, it's like a backward proof. Okay, if it's not true, then this gradient f could be written as uh, summation lambda I times gradient hi, and we can add another term, same some arbitrary term, but this arbitrary term is a vector. Okay, so let's call this vector u, some u vector. Okay, so because three is not true, then um, that means the equation three is not right. So if I add some, so that means there's a difference between the left hand side and the right hand side of this equation. So the difference could be named as u. So if we can show actually u must be zero, then equation three must be true, right? That's how it's gonna be proved. Okay, so in this case, of course, because the initial argument is that three is not true, so this u vector should not be zero. So u is not zero. Okay. Over here, but it's a component of gradient f orthogonal to. So let's this u vector. It's let me see how this could be. This u vector is quite important. Why is it orthogonal to u dot gradient h equals to 0? Let me see why. U dot h. Okay, so um, lambda is actually something we don't know, right? Lambda are just a bunch of numbers. So when we formulate this equation 3, we never said what are lambda. Lambda are just numbers. But later on, I will tell you they are so-called the Lagrangian multipliers. Um, but we never said what are lambda. So they're just like coefficients that trying to make this equation 3 satisfy. Okay, and when we try to reversely prove this, we claim what if it's not true? We have um, some u vector at the end. So now we have the opportunity to define what how u is behaving. Okay, so when we define this over here, we define uh, because lambda could be anything. So u could also be anything, right? So if we define u as some vector that is orthogonal to the gradient of h, okay, we can do that because the weights lambda could be changing. So let's say u is only has one property, which is orthogonal to gradient h. So if this is happening, that means um, u dot gradient hi equals to 0. So that's the only thing that we define by ourselves. Okay, so now we can do some tricks because we would like to study uh, how uh, how the equation 1 and 2 look like when we apply them to equation 3. So from we can do this, the d dot, we can check d dot what? Gradient f. Let's check this one. Okay, let's check this. So when we check this, since in this argument, in this process of the proving, we said this gradient f equals to the summation of lambda I times gradient hi and then plus u. Okay, and this has to be 0 because we want to satisfy the rule number 1, right? So we want this to be less than 0. And then we can expand this whole thing. This is uh, so basically lambda 1 d dot gradient h1 plus da 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 plus lambda m d gradient d dot product with gradient hm, okay, and then plus d dot product with u, okay, and in this case all these actually are zero because of the rule number two, because of number two, right? And from here, we said this whole thing is smaller than zero, right? So we found d dot u is smaller than zero. Okay. So the next thing that we do is that so u is something we don't know, but we know it's perpendicular to gradient h. Okay. And the next portion of the proof is that we um, let's say if we set uh, d equals to negative u. That let's say if we do that. So that's another if that we did. Then we have negative u because d could be any moving vector, right? So u could be one of the moving vector. Okay, so let's talk about and this the way this is arguing is that if this rule satisfy all situation must satisfy. So they are trying to pick up some situations that will break the rule. That's why they want to talk about what if d now is negative u, and let's see what happened, and then that actually will break what we had at the beginning. So from here, we will have this, right? Because and this shall be negative at this point. But if we have so that means uh, we could so d is basically the uh, what should I say? Mm, d is a vector that help you to find a new point. Okay, and uh, oh, I actually would like to do the other way. Sorry, it should be like this. Sorry, d dot d. So basically, I change. It shouldn't be the u one. Should be the d one. Okay. So from here, it's like then you have d dot d become positive. Okay, so it's like uh, the only chance d dot d is positive is that d is not a zero vector. So in this case, then this means d is not a zero vector. So d must exist. D must exist. So if d exists, that means you can find a better solution than x star. So that means your x star is not x star. So only chance. So that actually breaks the entire uh, the hypothesis because the hypothesis is that um, the three equation three is not true, right? So and you at the end you can tell your x star actually is not your x star. Okay, so that means our hypothesis is wrong. So what is our hypothesis? Our hypothesis is this argument, and at the end of this uh, proof, we have a conclusion that if this hypothesis is right, X star is not X star. So our hypothesis must be wrong. So if our hypothesis is wrong, then hypothesis was wrong. So 3 must be true. Equation 3 must be true. That's how this is being proved. Okay. So that's why when I tried to introduce equation 3 from 1 and 2, I didn't uh, use any reasoning to introduce 3 because it's so indirect. It doesn't, if you understand 1 and 2, it doesn't automatically tell you, hey, I figure the 3 must be true, right? So that's why we're not mathematicians. Only mathematicians are that smart. But at least we can learn what they found. Okay, so and over here they found in optimization, uh, the first equation represents how a method finds a better point to satisfying optimality, and the second equation tells us how optimization try to find a feasible point. And how about the third equation? The third equation tells us this is a very unique rule that the optimal point must satisfy. And that was proved with the 1 and 2 equations. During the proof on at the bottom, see how we actually mention we assume equation 1 and 2 are true. So see we over here we mentioned about the equation 1, and over here we mentioned about the equation 2. So the argument, the proof at the bottom already assume 1 and 2 are true. Okay, and then we use what we had earlier in order to prove equation 3. So equation 3 now become very important property for optimization because that is something you can check um, if your point is a optimal. Okay, so now we could finally come back to the optimization problem while we want to talk about the initial problem. Okay, so we could now talk about KKT. Copy. Okay, and in the previous slide, we just showed uh, for minimizing f subject to hi equals to 0, we could have gradient f, gradient f x star equals to summation lambda I gradient hi x star. Okay, we have this, or we could rewrite this into a different way. Okay, so we could rewrite like this. So it could be like partial f partial xj, and then uh, we could convert all the lambda into negative lambda. Okay, so because we have never mentioned what is lambda yet, right? So lambda basically are just weighting functions. But for further discussion, now we would like to discuss in this way where all my lambdas are on the all my right hand side are written in the left hand side. Okay, and over here I have my hi and then xj, and over here summation on I equals to 0. We could rewrite like this, right? Basically, every so there are totally j equations, from 1 to n, right? So the first equation right here was in the vector form, but we can expand then into n equations. So the jth equation looks like this, right? Okay. So so that's something very important for later on, and we need to work on our the general problem here. Okay, this general problem actually just like what we did in linear programming, we could convert this whole thing into the uh, equality. Everything become equality. Okay, so uh, when we do that, we just need to introduce the slack variables. Okay, so let's introduce slack variables. Over here, I can keep all my hi equals to 0. Okay, but for my gj, I'm introducing some sj for each equation. In order to make sure my slack variable is positive, this time we could introduce some value sj square over there. So when I put into the equation, it's always a positive value, right? So that's how you could convert your gj smaller than 0 into a equality constraint. Okay, so here this is my slack variable. Okay, so that this knowledge was uh, introduced last time when we did the linear programming. But in linear programming, we want everything to be linear, so we never put s squared in our equation because that make our formulation becoming quadratic. But over here today, it's a general derivation about nonlinear programming. So uh, none of the equations must be linear yet. Okay, so there's no uh, rules about the order of the function at this point, and that's why you could play some tricks with your slack variable. And over here, we try to use s square to make sure uh, the slack variable term is always positive, and that save us some time to that has some benefit that you don't need to set up another equation to keep s become positive, because in this way s could be any number. Okay, so let's continue. So when we have all these, we could convert all of them into equality constraints. And over here, that's how about let's use capital H, okay? And we totally have because I originally has 1 to n, J has 1 to n. So when I merge all the equality constraint together, I have in total of n plus n equations, right? So we can just put them together. They are all equality constraints. And based on what we introduced in the last slide, we now have gradient f over gradient a partial f partial xj plus summation and then lambda I. Over here I have partial capital hi over partial xj. This must be zero. Summation on I, right? Because this is what we had earlier, and we wish our optimal solution satisfy this. Okay, and we just show our optimal solution will satisfy this. Okay, and now we we although we at this point we like to combine them together, so we could apply this equation to here. But after this applying, we want to convert the whole thing back to its original formulation. So that's convert back. Partial f partial xj remains the same, but for the capital H, we don't actually want to deal with capital H. We don't know about capital H. We want to handle small h and small g. So over here, that's apply substitute small h and small g back to our equation. So we actually have something like this. So here should be small h of I and then xj. Okay, over here, my I equals to 1 to m, right? Because I have m of them. But how about the other ones? The other ones are in the back. But for the other ones, let me rename them as mu. Okay, and over here I have gi plus si square over xj. And here my I equal from 1 to n of them. Maybe I make this larger. Uh, okay, so did you notice what I did? Because earlier we put h, I, and all these gj plus sj squared together. We put them together. Oh, maybe not this color. yellow. Earlier, we put all these equations together, combine them into this capital H, so that we can easily apply the equality. So we can easily apply this equation, this one. And when we had that one, we just put these two back to the original. When we do that, they have two different parts. Okay, this is a very important equation, so I would like to make it larger so you can keep a note, or later on or you can clearly see it. Okay, so let me copy it and move on to the next page. Okay, so paste it here and then resize it. Okay, so we now have this. Okay, a bunch of stuff right here, and since all the Si has nothing to do with xj, right? We are doing derivatives, but Si has nothing to do with xj. So the gradient of that part, of course, is 0. And of course, Si squared has nothing to do with xj. That's why that portion is 0. So that we could further reduce the complexity of this equation. And then we have this. I from 1 to m plus I from 1 to n. And here we rename this as mu. And over here, Gin x, xj. Okay? And of course, we have j. Oh, did we mention how many? We never mentioned how many x we had. So did I? Here. Sorry, I made a mistake here because n is the number. Small n is the number of my g right here. Small n is my number of g. So I shouldn't use this. Let me use capital N. So small m is number of h. Uh, Small n is number of g, and sometimes gj or gi, right? Just index. And capital N is my number of variables, so xj. Okay, so these three numbers are different. Okay, so that's why over here j is the representing the number of my variables. I should have capital N numbers of those equations. Okay, but oh, this is very important one. Let's draw a box. Okay, let's draw a box. So when we introduce our select variables, actually there are still variables of our um, uh, problem, right? Because when we do this, originally we have a bunch of x, but we convert to this, we just introduce several s. And how many number of s? Uh, for every gj, we have one sj. So the number of s is the same as the number of g. Okay, so we have a bunch of those s, and they are also the variables of this problem. So when we have this equation, supposedly this equation also uh, could be applied to our slack variables. Okay, so now we want to talk about for the slack variables. So we have xj, j from 1 to small n. Okay, we have those. Supposedly the expression looks like this. So here sj, right? So just uh, convert this equation to here. But at this point, we are doing derivative with respect to sj. So the only difference is that we're doing derivative over sj. The rest are the same. So, and there will be n capital N equation of those. Okay. So does f has anything to do with sj? No. So this one is 0. The objective function has nothing to do with our slack variable. Okay. Does equality has any function with it? No. So this is also 0. How about g itself? Actually, the g itself, uh, it has nothing to do with your slack variables. Only the slack variable itself has something to do with your s, right? So this gives us a conclusion. Uh, 2 mu I si actually equals to 0, right? If you do derivative, only when the index of I equals to the index of j, there has this term, right? For the ith equation, when if you couldn't tell, let me show you. So basically, you have a bunch of mu1 uh, gradient s1 square over sj plus da 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 mu1 s n square. Okay, so those must be 0. This is actually like this, a bunch of those summation together, and the sum we sum on I goes from 1 to n. That's why there are n terms of those, and we have only when the ith one equals to the j, only when I equals to j, this term has a value. So mu I partial si square over partial s. So I now equals to j, right? Equals to 0. Only this one is not 0. I'm sorry. Only this one uh, will be remain. The rest are 0. But still, this is 0. Okay? Because the rest of them become 0 by derivative. But only this one has some results for derivation. So what would be the result of this derivation? This, right? It's a coefficient of 2, and we keep in the uh, uh, we keep in the coefficient of mu, and because of s squared, we have a 2s. Okay, but we only have one term left. The rest of the terms are 0. But this equation equals to 0, so that conclude this term must be 0. Okay, and we will have how many of them? All of them, actually. So here for I from 1 to n or to j. Let me see. Uh, ah, should be small n. So I made a mistake here. Small n. Because we only have n of them. Our S only has n of them. So we have n those equations. So at the end, I have n of those terms, right? Okay. So that concludes uh, mu I S I must be 0. That's another equation that we have to satisfy. Okay. So that's already our. We have two equations for our KKT condition. There's one more. There's one more. Okay. So this is actually the first equation you must satisfy for KKT, and the second equation you must satisfy for KKT. Okay, and we have one more. Then we have all of them. Okay. Now, let's see how we could derive the last one. Okay. Let me see. You... actually, the second one doesn't help us. This one doesn't help us. Sorry. Why does it not help us? Because we don't care about slack variables. At the beginning, there's no slack variables. So we derive some rules about our slack variables, but if we never have those transformations in the original problem, we have no slack variables. So the rules about slack variables doesn't help us. Not yet. So this one doesn't help us. Not good enough. So that's why we need to do further discussion, and that will actually ends up with two more rules. Okay, so in order to change this rule about select variable, we need to do further discussion. So for about the further discussion, suppose I have a vector d is uh, feasible perturbation at my optimal. So again, it's like a movement, moving vector from your optimal. But it's when we say perturbation, it's like a very small movement, and that movement will move the optimal point to a new position, but that new position is still feasible. Okay, and and of course, in optimization, we want to keep optimality, and we want to keep feasibility. So based on what we introduced earlier, what are the rules? Basically, this is a d vector dot product your gradient f at your optimal. Uh, should it be negative? I remember we said we want this to be negative, right? Should should be like this, if I'm right. Mm, yeah, and then we want to talk about. Oh, hold on. Let me double check something. Ah, okay. Over here, actually, this guy. Let me make sure if I made a mistake earlier. Uh, yes. So so earlier we said we wish this at xk. We wish this to be negative. So so we could we could find a better xk plus one where uh, d is basically the movement from k plus 1 minus your xk, right? But what if we already reach the optimal? Then we shouldn't uh, keep the same rule because this is the rule for during the process. So the reverse of this rule basically becomes this. Okay, so that's one part that is a little bit different from earlier. Okay, and then the for the equality constraints, over here we are focusing on uh, because your h is 0, and based on the earlier derivation, we want this to be 0, right? Because that make sure if you move from your first current point to the next point, it remains feasible. So this must be 0. That's that's how you could satisfy the argument here, the feasible perturbation. And the other thing is here. How about your GJ? Over here, should it be, did we talk about G? G is always negative. So if you make a perturbation, uh, so let's say here is your G function. Supposedly here is your gradient of G, and here is your X star. And if you have a perturbation, let's say somewhere here, so this is like a D, right? And the gradient over there, the angle in between, uh, if it's positive, then you are actually moving out of the moving into the invisible space. If so, this is like the case of d dot gradient g positive, and if it's like a perpendicular movement, then in this case your d dot your gradient is 0. And over here, this is the case where your d dot your gradient g is negative. So from this observation, it seems like in order to keep your uh, uh, perturbated point neighboring at the neighborhood of your optimal, it seems like the movement d dot product your gradient g must be smaller than or equals to 0. Okay, so uh, this is how this we could have these three rules, and then we would like to apply these to what we had earlier. So we will apply to which one? Oh, so we would like to have this equation. Copy it, and let me move this one to here. Oh, I'm sorry, this was blocked. So let me. Okay. So let me paste this guy here. Okay, this is what we had earlier, and then we would like to uh, uh, have a dot product, have this whole thing dot product with D. So now let's try it. So dot product, and then we should have a gradient f, and we can keep. So our gradient is actually is we can use the gradient sign here plus summation of I lambda I. Every term has a d dot gradient h I plus summation I. So this is I from 1 to m. This is I from 1 to n. Mu I d dot gradient g I. This, of course, we wish it is still 0, right? Because the top equation is 0. Even we multiply something, it's still 0, right? And from the arguments here, we found this shall be positive, and over here, this shall be 0, and over here, these shall be negative. Okay? So in this case, the only chance that this equation could become, oops, sorry, only chance that equation could be zero is that these has to be positive. Okay, so mu could be anything because this is zero, and this is already positive. And when you sum everything together, this is negative. We of course need this to be positive. Otherwise, the summation of those couldn't be zero. Okay, so that's why we have new rules. Mu I must be zero. Must be positive, or zero, of course. Everything could be zero. Okay, so that would be our third equation that we came up with. Okay, and take a look at our second part. Mu isi equals to zero. Okay, so now we go back to mu isi. Mu isi must be zero. That was from the second part of our derivation. We know all the mu isi must be zero, and since gi plus si squared is zero, right? So there could be two possible situations. One situation is that si could be zero or si may not be zero. So what happened if si is zero, then or let's say if si is not zero, then mu I must be zero, right? Because we have to satisfy this. How about the bottom case? When si is zero, then uh, when si is zero, then gi must be zero, right? So over here, gi must be zero. Okay, so there are several different kinds of situations. Okay, so either mu I be zero or gi be zero, right? So that's actually the final uh, rule that we have. Either mu I be zero or gi be zero. But can we describe this in a mathematical way? Yes. When we say mu I gi equals to zero, they could both be zero or either one of them is zero. Okay, so that's how we could have our final, the four, um, the fourth equation. Okay, now we have introduced a lot of equations. Then let's put them all together. So to sum up, for a general optimization problem, for a problem like this, copy, paste. For a general problem like this, what does the KKT condition say? The first condition actually is this one. That's our first KKT condition. And over here, J from 1 to capital N. Okay. So the index J right here is xj. And on top, the J over here represents GJ. So I use the same index, but they are actually different. Okay. That's why this is a small case and this is capital A. Okay, so that would be the first condition we must satisfy. How about the second one? Second one is this one. Okay, how about the third one? Third one is this one. So if you could check all three conditions of your design point, and if they satisfy, supposedly this should be your optimal. Okay. Uh, what what time is it? So 4:30, right? Um, The next one I introduce actually is quadratic programming. And in quadratic programming, it's important that we use KKT condition. But I think we don't have enough time for quadratic programming. So how about we try to evaluate some problems using KKT and let's see what happens. Okay, so let me create some problem. So let's say we are minimizing x1 squared plus 10 x2 squared. Uh, I better find a problem that I know the answer. Okay, so let me use some graphical trick to figure out. Um, so if I have, let's say, x1 must be 5. So here is 5. So this is my G G1 equals to so I should write it in a better way. This is my H1. H1 is uh, x1 minus 5 equals to 0. So my H1 equals to x1 minus 5 equals to 0. Okay. Let's try to do some optimization on top. So I know my gradient is going this way. So in order to find a solution, maybe I've chose a point here. How about some constraint like this? So the equation will look like x2 equals to 5 over 1 over 5 x1 So I would like to the top, so larger than or equal to. Yep. So some equation like this, and I need to rewrite in a different way. So let's say 5x2 larger than x1, and so x1 minus 5x2 smaller than 0. So this is actually my g function. So I guess I don't have other equations, so I'm gonna erase the 1 right here. So just one uh, uh, equality constraint, and another one is a inequality constraint. So I know the solution should be this guy. This is 5 and 1. So 5 and 1s should be my optimal. But let's evaluate some other points. Okay? Before we evaluate, let's formulate the equations. So based on KKT, I should have what do I have? So gradient f plus mu gradient h plus mu, that was lambda, and now it's mu gradient g. This shall be 0. And what do I have? Mu, I should only have one mu, so my mu g needs to be 0, and mu has to be positive. So if I could satisfy these three, then that point should be my optimal. So let's try some design point. Let's say 2, 2. How about that? Okay. So for the first equation, maybe I evaluate all the gradient first. Gradient f is 2x1 and 20x2. Gradient h actually is 1 and 0. Gradient g is 1 and negative 5. Okay, so let's try. My gradient f in this case is 10 and no, not 10. 4 and 40. So plus lambda times 1 and 0 plus mu 1 and negative 5. This equals to 0. So we could actually solve for lambda and mu. So I could multiply everything by 5. So 20 plus 5 lambda. Actually, in the bottom one, I already know what is my mu. Mu is 8, right? In this case, mu is 8. And what is the function value of g? G of my x in this case is x1. My x1 is 2 minus 10. So this is negative 8. So my mu g in this case equals to negative 64. So doesn't satisfy. Okay. So from here at the bottom equation, I got value of mu, and the g I just plug in, I found is negative 8. And when I multiply, it's not 0. So this is not optimal. Okay, and let's try other point. Let's try supposedly I believe this is optimal. Let's try 5 and 1. When I evaluate the gradient, I have 10 and 20 plus lambda 1 and 0 plus mu 1 and negative 5. This needs to be 0. So in this case, quickly, I know mu is 4, right? And how about my g? My g, I plug in 5. 5 minus 5 is 0. So my mu g is 0. Okay? So this one is good. And my mu is positive. Second one is good. And you can plug back to the first equation. You can always get a lambda. So that means I can always have a lambda which satisfies the first one. So this must be the optimal. This is optimal. So I think for me, when I first learned this KKT condition, I feel like it's magic. We spent more than 2 hours to derive a bunch of equations from this argument to that argument. And then the 3 checks are so simple. Just doing this, and that, and then plug in the numbers, see if they satisfy. If yes, it's optimal. If not, try other points. So I think it's quite interesting. Okay. Um, Remember we did solve a linear programming problem, right? Did we uh, did we have an original problem? Oh yes, we do. We do. So maybe I give you a homework of asking you to check whether the point is optimal or not. Okay. So maybe I give you a homework. Every time I give a homework, I worry if there's truly a solution or not. Okay. So minimize. Let me open my MATLAB just to make sure. I want to give you a problem that truly has a solution. Oh, by the way, is it important to be able to derive what I did today? The true answer is no. So the derivation for today is just for you to know how some optimization methods or rules were derived by the mathematician. And if I just tell you, hey, do this, do that, you're just undergrad. But you're graduate students, and even many of you are PhD students. It's my responsibility to derive and to show you and make sure you can kind of understand during the process. And for engineering, I should say for optimization user, maybe it's not important for you to derive those. But if one day you would like to derive or to create some methods on your own, like myself, actually those actually kind of help. So let's say in the first time when I took the course, I couldn't, I could never imagine, I, I, I couldn't have this figure in my mind at the beginning. But nowadays I know because I know it's like this. And maybe it's because I have a deep understanding of all those derivations, and then I know, oh hey, I can actually explain to you by this figure. so that I don't need to go through so many wording or proof. This works. And that kind of sense about those math, calculus, and vectors and rules actually helped me on developing methods. And I wish today's introduction could help you as well. Maybe not right now, maybe hopefully someday in the near future. Okay, back to optimization. So let's see. Blah, blah, to this one. Okay. Uh, okay. So let me easy contour x1 square plus 5 x2 square plus 6 times x3 square minus x1 times x2 plus 10 x3, and maybe that's enough. Oh, you can never see the contour. It's a 3D problem, so maybe isosurface. Isosurface. Let's see. Try. Okay. Uh, Let me figure out. It's very nonlinear, so maybe I try different region from zero, everything from zero. Let's see how it look like. Okay, so the objective function looks like this. Should be okay. Oh, you don't see it. The Facebook doesn't see it. But am I streaming still on? Okay, good. So here, let me modify a little bit. Hold on, hold on. Uh, Let me see how I could just share the screen. Uh, this. Oh, okay. I have. So it will went crazy. Don't do that. I need to crop it. Crop. Oh, it's about 500. Okay. 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 Good. 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 So yes, and get rid of this one. Okay. So yep, my MATLAB here, and I don't need this here. The object function looks fine. Then what's my objective function? It's minus x1, oh, minus x1 plus, oh, minus x1 times x2. So this time I create a coupling term. When you have coupling term, you need to worry about whether your solution, uh, whether you have solution or not. But when I observe how the function look like, I think it should be fine. Cross the fingers. Okay, now, so I wish we could study on some point completely inside this domain. So, what is my domain? Uh, so x1, x2, x3, they are all larger than 0 or smaller than 5. Okay? And let me draw a planar surface. So it's our point should be on the planar surface for all times. What could the planar surface look like? So let me do a hold on, and then let me draw another function. This time I do a iso surface. Yeah. Uh, Let me recall my function browser. No, 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 not this guy. Let me open. Uh, Same domain is fine. So same domain, and what else? Number of just one of them, and f is string. Just give empty, and then 0. Can I do that? So let's try plus x2 plus x3. How about equals to 5? I'm not sure if that works. No? Can I do that? How about this? Okay. Did you see a plane? But that plane was not the one. Um, what did I? Let me see. I think I could. Let me see. F extreme. Ah, that's the one. So get rid of this one. So that was the one I wanted to draw. So I have a plane cutting from these points. So I need this to be larger than this. So the function is so x1 plus x2 plus x3 must be larger than 5. Then I will have a plane like this. And imagine, how about this? Let's make it an equal sign. So basically, you are trying to find a point on that surface. And if there's no further rules, what would be the minimum point? The minimum point should be here, this corner. Because following the contour, uh, this side should be having, oh, maybe not. The blue is lower. So this contour is representing the lowest value. So going this way on the left lower corner, we should have the where the optimal is. And maybe I could define some other rules. Let's say, um, how about something about x1 and x2? So if I say like something like this, uh, maybe x1 square, so it's like x2 must be larger than x1 minus 2 square. So what does it look like? Let me draw it. Uh, so if I need to draw this, then it has to be like x1 minus 2 square minus x2. This should do it. Okay, so I just it looks like a mess, but it's it's like a curve like this, and I want this to be larger than. So it's like we are focusing on a domain like this, and my rules will one of the constraints is that I am trying to you basically is trying to find a point on a planar surface like this. So basically, that's one of the equation you have. Oh, not that corner, but anyway, if you rotate like this, yep. And in order to so it's like on top of that uh, planar surface, it's like you define a boundary. You define a boundary, and only what's inside the boundary is a feasible point. So it's like you are trying to find um, some value inside this purple area, and your based on my observation, your solution should be somewhere here, I guess. So I guess your solution should be somewhere here, based on how the objective the trend of the objective function. Okay, but I don't actually know what's the solution. Maybe I should solve it and tell you what is the solution, and then you check it by KKT. Okay, and maybe I can use this opportunity to show you how this could be solved by MATLAB. Okay, let me see. If I want to solve it by MATLAB, I have all the equations. Um, let me see if I have. Hmm, so let me show you the screen first. Okay, and then you can copy the problem later on. Let me show you the screen. So in MATLAB, I may need to open a new script. Okay, and over here, I uh, will start with an initial guess. So the initial guess could be something like a 555. And then I'm gonna use something called fmin_con to solve it. So what does fmin_con means? Function minimization, con means constraint. So it's like a constraint minimization. And it's a function that MATLAB has. Okay, and over here is you need to write a function on your own, and then plug in your initial point, and then ignore this part. So give an empty input, ignore this part also here. Lower bound and upper bound. My lower bound basically is 0, 0, 0. My upper bounds are 5, 5, 5. And then I need to write a code about my constraints. That's all. So save, and let's call this, let me save it somewhere. Maybe my desktop. So test.m. Okay. But let me make sure. Change path. I I need to specify my function and my constraints. So how does MATLAB work on this? You need to create a new file, another script, and over here you say function and say y equals to my func and x. So where this file name is going to be named as my func, so basically my function. And over here, in for fmin_con, you specify the name of the function that you describe your objective function. So over here, whenever fmin_con needs to evaluate the objective function, it will actually go into this function. So when we are in this function, we can write down what would be my objective function. So x1 square, but you need to write in this way so that admin can recognize it. Plus 6x3 square minus x1 times x2 plus 10 times x3. Okay, so this is how you could describe your objective function. Save it. Done. And then you open another file, no, create another file. And this time you say function, but you need two outputs. Before I continue, I just want to double check fmin_const. So check the help of fmin_const, and it actually teach you how to do it. And over here, here. So the first output is the values of inequality constraint, and the second one is the values of equality constraint. So C and uh, CEQ. So that's just how they would like to name, but it doesn't matter. You can name it in the other way. But I will just follow, and I name my function as mycon because in my uh, main code, whenever I want to specify my nonlinear constraints, I will ask this function to go into this additional file in order to evaluate all my constraint values. So over here, I need to specify my equality constraint. So the value CEQ will equals to what? X1 plus x2 plus x3 minus 5. How about my inequality constraint? This must be smaller than 0. So x1 minus 2 square minus x2. This must be smaller than 0. Yes. So save it. We can run it. Already finished. And what's my solution? That's the solution. Okay. So if you by fmin_const, we know the solution is. You can go back home, and one of the homework is to check to show this is the solution. Okay. One of the homework. So use KKT to check this point. Okay. MATLAB said this is optimal, but to be safe, we could actually kind of visualize the iteration process. So let me explain to you how you could do it. Over here, you could open some show some output. Let me see how. It's called options. Here. You could have options for your iteration process over here. Options. And your options needs to be defined. What happened? Why? Time to go? Why? Did I do anything? Okay. I know we all want to go. So you could, let me see. Uh, my live broadcast was a little funny right now. Anyway, let me quickly finish in the class. Uh, for MATLAB, you could specify some options. So the options could be defined here. And I think you just need to display the iteration. Yep. Run. Okay, so from here, it actually utilized 11 iteration to converge, and you can see the feasibility is always positive right here, and then it become negative, but very small. Positive. They are all positive, but becoming very very small, like a 10 to the power of negative 12. For the optimality, it's also remaining positive and it's becoming very very small. Okay, so when they are zero, then you can no longer improve. The objective function value, you can see it doesn't change much at the later steps, and this is like how much movement it's having. Like almost at the bottom half of the iteration, it's moving so small. The step size is like 10 to the power of negative 7. Okay, but it doesn't show the points. We want to see the points. So we could also initiate some let's make some drawings. So in order to do that, figure, and then I just erased it. So easy iso surface. So my plotting zone should be like this, and my function is this guy. But in here, I need to specify in text. Oops. Okay. And also, whenever we evaluate, let's plot 3, x1, x2, and x3, and then plot a small like a dot color, red color, and the size. Let's make it larger first. Marker size 10. Save. And here I said hold down. And I also need that particular file, uh, easy iso surf. Okay, I need to save that on my desktop. So I could use it. It's a function I wrote in the past to show iso surface. Let's see. Too small. So the marker size has to be way larger. So maybe 30. And then draw now. It's too fast. Okay. Initial point is what? What's my initial guess? 555. Where's 555? I didn't draw the 5. Did I draw 555? Let me do it again. Step. So F Min Kang didn't try 555. How come? So F Min Kang is trying some other method. I don't know what method it's using, but it's testing 444. I don't know why. Okay, and then let's continue. Step, then step. What's okay? Let's continue to try. So anyway, MATLAB tried several points until it kind of converged somewhere here. Okay, but it's hard to tell what happened if we don't draw the constraint. So let's also draw the constraint using the same function. We have this one. Okay, and let's take a look. Ah, sorry. I need to, play with this function. Otherwise, there are too many contours. Okay, so now let's take a look. Did you see how MATLAB was able to find some points right on this plane? Okay, so the solution was 3 point something, 3 point something, and then 1 point something, and then 0.0. So it's like somewhere here. For some reason, the solution is not x3 doesn't equal to 0. I don't. Maybe some of my we can only tell by. Let's try to draw the parabolic to see why x2 minus x1 minus 2 square. Okay. Maybe we could hide our contour. Come on. This guy? Let me. I need a figure palette. Oh, here. Uh, Not this guy. Plot browser. Yes, plot browser. So I can hide my contour. There are too many of them. Okay. So let's see what happened. I need to rotate here. Aha! So during the process of optimization, did I make the equality correct? Hold on. Uh, Equality. This is equality. Yes, this is inequality. Yes. So Why did MATLAB try to start from 444? Did I? Should I switch this? Hold on, let me double check. Let me switch this and then solve it again. Oops. Here. Ah, the first one was right. This one was wrong. Equal. Okay. So run again, and then view in the plot browser, hide the contour. So from here you can kind of tell MATLAB was starting from some point here. Ah, maybe it's because my initial point doesn't satisfy the equality constraint. So MATLAB using some other way to choose maybe a better point for him. I don't know how, I don't know what was the exact method MATLAB used, but MATLAB was starting from this point. And then the iteration, as the iteration move on, uh, eventually it reaches the corner over here. Did you tell? Can you see this corner point right here? That point is on the triangular plane, and also on top of this parabolic curve. And our inequality constraints said we must be finding some point on the right hand side of this curve, and our objective function is pushing the point to that corner. So that's where we are able to find the minimum value within the feasible space. Okay, so these are just some ways for you to visually check what happened. Otherwise, for high order problems, it's sometimes really difficult for you to know whether this solver is giving me the right answer. Sometimes you just don't know. Okay, so please go home and check our solution here. Let me do this. And please also check. Oh, you couldn't see it. My software screwed up. So see here. Uh, it's gonna delay for 10 seconds. Please also check some other point, some other point uh, by yourself. Okay, just pick a point. But remember, when you try to use KKT condition, the variable upper bound and lower bound are also considered as inequality constraint. So there are actually a lot of, there are already 6 of inequality constraint. This is only one. This is the 7th. So there are totally 7 inequality constraints, 1 equality. So you need to follow what we introduced earlier. Follow what, sorry, this is streaming, so it's gonna delay for 10 seconds. Okay, so you just need to follow what I did earlier. But in my case, I only work on 1 inequality constraint. For you guys, you have 7. So when you do the gradient uh, of G, you basically have 7 of them. So why don't you go back home and check, see if you can do it? and handing next week. And let me remind you, after one more class, we shall have another exam, and I will tell you what are the most important problems in that exam. First will be the linear programming, so just like what you handling today. And the second thing is using KKT to check optimal. Okay, so last week and this week will be covered in the exam. So please remember, please make sure you know how to do it during the exam. About next week, I will introduce quadratic programming. Quadratic programming is hard for you to do it in exam, so probably you don't need to do it in the exam. Okay, but quadratic programming is still very important for the course. Okay, see you next week.